So before applying any routing algorithm, so the concept is initially the routing table of a router is empty. So basically the router is a device which is connecting the networks, okay, the multiple networks. So just to place a router on one side one network, on the other side another network, if you join with the cables with the router, then the router will not know immediately the systems in the networks or the device in the networks or the routers in the network. So what I can say, initially the routing table of a router is what? Empty. So for example, if I have taken, suppose say A is the router, then here the table will be what? Empty. It will not have any information. Say for example, after some time, suppose the router A, okay, is connected to, suppose a router B. Initially it is empty. Now suppose it is connected to B with suppose a 4 units. Then here the one important point is, what the second statement is, every router will be knowing the information of directly connected routers. So for that, no need to apply any routing algorithm. See, router A is connected to router B with 4 units. So A will be knowing about it directly and B also will be knowing about A directly. So then it is going to have the table. So how the table of A will be? So it will be in this way. What does it contains? It will be like this, A to B. So A to B means what? The destination. Okay, A to B will be there, and here we can call it as the estimated delay. You can call it as the estimated delay, and this you can call it as the next hop. That means with help of whom the A knows about B. Now see, A to B, how many units it is? Okay, or you can say, in fact, this B, you can write one more point you want, because below you can written as D. So this you can call it as the destination if you want. So what is the destination? The destination is what? B. So A to B. What is estimated delay? How many units it is? It is 4. Who is the mediator? Mediator is nobody. Directly it knows. So it is dashed. That means what? A knows about that B with 4 units and it knows directly. So the mediator is nobody. Same thing will happen to the B also. So what we have told? I have told you two statements. Initially, the routing table of a router is what? Empty. Second statement, what I say? Every router will be knowing the information of directly connected routers. Okay, fine. Now, see, for example, if we have taken that same diagram, suppose see the router A, then it is connected to router B. How many units? It is 4. So A is having the table. So what is that particular table initially it is having? A to B, how many units? It is 4 units. How A knows about that B? Nobody, it is dash. So after some time, and you know this you can call it as the destination. Okay, this is nothing but what? This is the next hop, and this you can call it as the delay. This is the next hop. Suppose here after some time, suppose a node C is connected to A. Okay, suppose say it is what? 1. Then as per the second statement, every router will be knowing the information of what? Directly connected routers. So it will know about that C. So here I can written as C. So in this diagram, we are bothering only about router A. If you want, you can try for the other routers also. So A to C, how many units? 1. How A know about that C? Nobody. So it is what? Dash. Okay. Now after some time, what happens is this diagram, suppose say it is modified like this. See A to B, it is 4 units and it is C and this is the value 1. So here what happened? A packet came from outside. That packet will have source address and the destination address. and here the destination address of the packet is B. So the packet came. So the concept is this packet came to router A and the packet is telling to router A that my destination address is B. Then what does A will do? A will store this packet in its buffer. And what is the destination address here? B. Then A will consult its table. What is the value here? B. How many units? 4. How you forward? Directly. So A is going to forward the packet like this. So packet has reached to destination? Yes. So this table is what? Correct. Like that we have to give the analysis. Now see the logic. Now the point is the table is the previous case. Here what is the table? C and 1 and suppose see after some time it is connected like this with 2 units. So whatever you think A to B which is 4 units, is it correct? Logically it might be correct, but if you observe the common sense, here there is some other alternate path to A to B, 1 plus 2 is 3 which is smaller. So that you have to update. So how it is going to update means, or the concept is, C knows that the B is directly connected. So that is C to B, how much? It is 2. Then after some time, this router C will tell to A, or C will forward to A that I know how to reach B and that value is 2 units and I am sending to you. If you want, you use it. That is the meaning. Now when C sends to A that I know how to reach B which is 2 units, what does A will think? If I forward a data to C, who will take responsibility? C only will take responsibility to reach up to B. Like that it will think. So 1 plus 2 how much? 3. But existing value how much? 4. What is smallest? 3. So it's going to be updated. So how it is going to be? Here it is updated. It is updated as what here? You can see B. How many units? 1 plus 2 how much? It is 3. And how he knows with the help of C? So this is the value. Okay. Now see the logic. Whenever a packet came to router A, in this case, the source address and the destination address. Let for example, the destination address of a packet is B. Now once a packet came to router A will store this packet in its buffer. Okay. And A will consult its table. What is the destination address? B. How many units? It is 3. Who is the mediator? C. So A will forward that packet to C and from C it will forward to B. Understand now? Now see from this diagram and this diagram, what is your observation? The destination address of the packet is same only. But in this case, the packet is forwarded in this way. But in this case, the packet is forwarded in this way. Now what you understand? In these two cases, even the destination address is same. What is changing? Path is changing. Means what? It is a dynamic algorithm, you can say. That means when you find some other alternate from this diagram, when you find some other alternate path, then the router has to update that new value. Then you can forward via that new path. Okay. So this is what exactly the dynamic algorithm. Why do you call dynamic? Because path is changing. Why path is changing? Because you find some other alternate new path and that is updated in the table, then only you can forward. Understand? Even if you find some other alternate path and if you don't update here, then A will be end up with forwarding via the old path only. So here the concept is, even if you find some other alternate path, okay, and if that is not updated in the table, then you may not be forward via the new path actually. Now here one important point is, in this case it is B, here also it is B. Now here this value initially it is 4, now it is modified as 3. So that's why here we call this 4 as the estimated cost. We say this is call it as the estimated cost or estimated delay also you can call. But now this 4 is modified as 3. Now you can call this as the final cost, you can say. Until if you don't find some other alternate best path. So here the point is, when does this estimated cost will converge towards the final cost? Means converging means moving towards. Means here you see the estimated cost is converged to final cost. Means what? When you find some other alternate path, you can say. Or you can say when the roots are converged. We use a term called when the roots are converged, then the estimated cost will be converging towards what? Final cost. So we have explained you two statements. Initially the routing table is what? empty. Second statement is what? Every router will be knowing the information of what? Directly connected routers. Now, if you still extend, because we have to give the definition of the distance vector routing. Now, what is the path here? It is A to, it is B, and C is connected. So, it is given as 4 and it is 1 and this is 2. This is the path we are having as from the previous diagram. Then what is the table of router A? Okay, what is the table of router A? So A to B, how many units? It is 3 units via which path? C. And A to C, how many units? 1. And there is no mediator, so it is dashed. Okay, understand? Now see, after this diagram, suppose this diagram, a new node came into picture. For example, see, router A is connected to router B, then router C. These all are the routers in the WAN area. So it is 4, 1 and 2. See, we are bothering only about the table of A. Now, for example, another node D is connected newly. Okay, in this way it is connected. Suppose say it is 1 and 1. Tell me what will happen. So the concept is, whenever a new node is connected, as per the second statement what I have told, every router will be knowing the information of the directly connected routers. So regarding this D, who will know first? Only C and B will know, because C and B, they are directly connected. So how it will be updated? Suppose say I can write C to D is equal to what? 1. Here also I can write B to D. How much it is? What? 1. But here one important point is, already A is having in its table regarding B and C. Now the question comes, when a node D is connected, does A will know immediately? Answer is what? No. Why? Because for A, this D is indirectly connected. Then who will know? B and C will know, because they are directly connected. So now the concept is, so in the next iteration, this C will send to A telling, see, I know how to reach this D and I am sending to you. If you want, you use it. That's why you can also call this as the routing by rumor also you can say. Same like that, this B also will send it to A. See, I know regarding that D and I am sending, and that value is 1. If you want, you use it. Now observe the logic here, it's quite simple. So already it is having the table, so routing table, what is the value? B, 3 and C, 1 and dash. Now it is talking about D. Now when B sends to A regarding the D and it is 1, what does A will think? If I forward the data to B, who will take responsibility? B will take a responsibility to reach a D. So 4 plus 1, 5. Same like that, 1 plus 1, how much? 2. So 5 and 2, which is smallest? 2. So it is going to update as what? 2. But how A knows? With the help of what? C. Then A is going to forward the data to, in this way, if you get any packet, just come asking for the destination D. So like that, now you see A knows the complete information about all routers in the network. Okay, then you can say it is a converge, you can say. Now this is the actual distance vector definition. Now that is the third statement. The third statement, every router will get the complete information of the network only with the help of neighbors. See, A has got the information regarding the D with the neighbors called B and C. So this is what exactly. Suppose for D, suppose you connect E. Regarding that E, first D will know, next B and C will know, next A will know. So this is the actual definition of what? The distance vector routing. What we say that every router will get the complete information of the network only with the help of what? Neighbors or neighboring routers, you can say. Not only A, remaining all nodes also will be knowing about it. So now if we talk about some theoretical statements. So if you observe regarding this particular D, C knows about it, that you can call it as the C to D as 1. So C will update as a routing table that C to D, how many units? 1. Who is the mediator? So nobody, so it is a dash. So it is going to update as a table. So any packet came to router C, and if the packet is asking for D, it will forward via to D with the help of this table. So this table, whatever C has updated, now it is acting as a output. But after some time, this information is sent to A. That means whatever the table which is output, now it is acting as what? Input. And then A has to, it is given to A, and 1 plus 1 is 2, it is updated as 2. So here the concept is what? Previously, whatever it is output, it is given as input. Now it is a output, again it is given as input to some other router. So that's why this distance vector routing, you can also call it as the iterative algorithm, because you can see the output of the vector table is given as input to other routers. Then other router are also updated with the new value, you can say. So that's why it is called what? A iterative algorithm. You can note down that statement. It is also known as a iterative algorithm, because the output of the vector table, is given as input, then that router also will fill with the new entry. That router are also filled with the new entry. Okay, now here one more point is, see this D is, this C is knowing about that D, same like that B also will be knowing about that D. So after some time, the output tables of this D and B also, they are sending to A. But observe, in the practical scenario, the routers B and C may not be at an equal distance to A, so that they will give this information at the same time. Or there will not be any global clock to this, so that they will give at the same time. That's why it is called it as a asynchronous protocol also, you can call, or asynchronous algorithm, because the router A, it is getting the information regarding that D with the help of neighbors B and C at a different time intervals, may not be exactly at the same time, because they may possibly at a unequal distance, you can say. You can note on that statement also. It is also known as the asynchronous algorithm. It is also known as the asynchronous algorithm, because from the neighboring routers, it is getting the information, at different time intervals, So you can also call this as the Belmont-Ford algorithm also, you can call, because this has been given by these two people. So you can also call it as the Belmont-Ford algorithm. The other point is, now what is happening when a node is connected? Regarding that node, a table is created at node C. Same like that, a table is created at node B, like D1 and dash. And after some time, table is also available at node A also. That means regarding this node, every router, they know the information about that router. So that's why, is it a centralized algorithm or a distributed algorithm? Means what you say, it is a distributed algorithm, because regarding a node, it is available information one after another at every node. That's why it is called it as a distributed algorithm. Okay. Sometimes in the question they don't mention as the distance vector, they will mention as the distributed algorithm. Note on that statement. It is also known as the distributed algorithm. Because for a particular node, it is known to all routers. And the tables are updated in the routing tables. tables are updated in the routing tables at different time intervals. So distance vector routing algorithm works fine when the links are properly connected. But there is one problem: whenever the link is broken, there might be a chance that you may get a problem called count to infinity problem. What exactly, how you get that problem, how to solve that? Now we are going to discuss that problem. For example, see, I have taken some network, like suppose say router X is connected to, suppose say, router A, then connected to router B. Okay. So initially all the routing tables are empty. Suppose here I have taken 1 and 1 as the delay. So when a packet came to router A, so the source address and the destination address will be there for a packet. Like for example, the packet destination address is X. Then it is going to update the table. Okay, since for A, this X is directly connected, A will be knowing about that X. For that, no need to apply any routing algorithm. It's going to update as X, 1 and dash. Okay, understand? So the packet will be forwarded to X. Does the packet has reached to X? Yes. So this table is right or wrong? It is correct. So here we don't have any problem. So this is case 1. So data has reached what? Safely. Say for example, now this particular diagram, suppose say X connected to A, okay, then connected to B. Suppose it is 1 unit and it is 1 unit. Right now this is the table of A is having. Okay, so what is the table? So it is X, it is 1 and it is dash. Now let, for example, next time, that is the case 1, it is the next time packet came to B and it is want to go for what? X. So this is case 2, but the packet came to router B. Now tell me, to the router B, A is directly connected and the packet is asking that I want to go to X because the destination address is what? X. So tell me, as per the rules of distance vector for B, this A is the neighbor and A knows about that X. Yes, because with the help of the table. So as per the rules of distance vector, A will tell to B that I know how to reach what? X. How many units it is? 1. Okay, understand, it is 1. So it will forward that. Then what does B will think? If I forward the data to A, who will take responsibility up to reaching X? A will take the responsibility. Okay, understand? So it's going to update the table. So how it's going to update? B to X, how many units? 1 plus 1, how much? 2. Who is the mediator? A. So it is a table. So based on the table, B will forward the packet to whom? A. So from A, who will take responsibility? A will take the responsibility. So does the packet has reached to destination? Yes. So this table is right or wrong? It is correct. So we don't have any problem here. Okay, so either in the first case, either second case, we don't have any problem. Tables are correct because packet has reached to destination. But what I told, whenever the links are broken, there might be getting a problem called count to infinity problem. So what exactly, what is this count to infinity problem? Okay, what exactly this count to infinity problem in the distance vector routing? Okay, that we have to analyze. Now, for example, see, suppose now this X is connected, that is this is the third case. A is connected and to this A, router B is connected and it is 1 and it is 1. Second case is also done. Suppose the packet came to router A and the packet want to go to X. At that time, the link is broken here. So as per the rules of distance vector routing, you tell me, if the link is not broken, then who are neighbors to A? Both X and B are the neighbors. Now, since the link is broken, who is the neighbor to A? Only B. And as per the rules of distance vector, B will tell to A that I know how to reach X as per this table. You can see B is having this table. B to X, how much it is? 2 units. So because that is the rule of distance vector. Now once B has sent, that I know how to reach X, and he'd send it as a 2. What does A will think? If I forward this packet to B, who will take responsibility? B will take a responsibility. So it's going to update the table. What? X. How many units? 1 plus 2, how much? 3. Who is the mediator? B. That means A is thinking, if I forward this packet to B, B will take a responsibility to reach X, but that is false. Why? Because the link is broken and there is no other alternative link also. How it will forward? But as per the rules of distance vector, you are following. So what happens here? So A is forwarding that packet to B, thinking that B will take a responsibility. Now see the logic. See, with respect to B, whatever this new packet is coming, it is a new packet. So as per the rules of distance vector, tell me, for B, who is a neighbor? A is a neighbor. Then A will forward this table telling, I know how to reach X, which is 3 units. Then B will think, if I forward this packet to A will take a responsibility. So it's going to update the tables. How it's going to update X? How many units? See, 1 plus 3, how much? 4. Who is the mediator? A. Then B will forward that particular packet to what? X. Now tell me, with respect to this packet, again this is a new packet. When this is a new packet, okay, it is going to update. What does A will think? It is asking for X. With respect to A, who is the neighbor? B is the only neighbor. B will tell to A that I know how to reach X, and that is 4 units. Then what does A will think? If I forward this X to B, who will take responsibility? B. Then it is going to update the table. How? X, how much it is? B is telling us 4 plus 1, how much? 5. Who is the mediator? It is B. Then again it is going to be forwarded. Now this process will continue. Once it is X, then what happens? It is again going to update, thinking A is going to update how much? X. How much? 5 plus 1, 6. Who is the mediator? A. Then again the packet it will come. So what is happening here? Packet is forming a loop or a cycle, and here you see 3, 5, then 7, 9. Here you see 8 to 10. Okay, so on like that, 101, and here this value will be 100. So on up to what? Infinity. So this is the what exactly problem. The packet will continuously rotate in a loop, but the packet will never reach to the X because the link is broken. So this problem you are getting in the distance vector routing, and that you call it as the count to infinity problem. The packet will never go to the destination. Okay, understand? So you can ask a doubt, in a bigger internet, only these 2 routers are filled with a wrong value, so on like that. Remaining all routers might be working. So how do you think that it is a big problem? Yes, it is a big problem because see, when the values are increasing so on like that, suppose the value is increased to suppose say 100. At that time for this B, suppose a router K is connected with a 4 units and a packet is coming for asking for X. So as with respect to K, this B is a neighbor at this time. B is telling, I know how to reach X, which is 100 units. And if it forwards, it's going to update the table as X, which is 104, and with the help of what? B, which is wrong, na? Because this is hardly at a distance of 6 only, it is updated. So this table is also wrong. This table is also wrong. This table is also wrong. So initially you may think only these 2 routers are filled with the wrong values, but other routers are also filled with the wrong values only. As the time progresses, the network will collapse. So this is the actual problem. So if you remember or not, when I explained you the IP protocol, I told you that whenever the links are broken, there might be a chance that routing tables are filled with the wrong values and they forward in a wrong direction, packet forming a loop. See, I have explained here practically how it will happen. When the link is broken, they are forward a wrong direction, so forming a loop or a cycle. So the tables are filled with the wrong values, and these wrong values are given as input to other routers because it is a distributed iterative algorithm routing by rumor. Then that router also filled with the wrong values. Finally, the network will collapse. So this is what exactly count to infinity problem. Okay. Now you will ask a doubt. Okay, this rotating for an infinite time is not at all a problem because we have learned in the IP protocol with the help of TTL value that infinite thing has become a finite one, na? Because it will rotate continuously. TTL value will decrement. At one point of time, TTL value becomes 0. The packet will be dropped. So there is no real problem for the data packets. That means what? Here the infinite looping has been bounded to a finite one. So there is no real problem for the data packets. They will rotate for a finite time. If this thing happens, and the packet will be dropped. Then why do you say it is a problem? The real problem is not for the data packets. The real problem is for the routers filling with the wrong values. So you have to understand count infinity problem is not for the packet forming a loop for the data packets. The real problem is the routers having the values which are unstable. See, 3, 4, 5, 6, 7, so on. It will switch continuously like that. Those are becoming unstable. The simple logic, what should be happen when the link is broken? A and B should have a information that it is broken as infinity immediately. But here it's becoming a quasi state, like 3, 4, 5, like unstable state is happening. And this unstable information is sent to other routers. So count infinity problem, the real problem is for the routers filling with the wrong values. That you have to understand. Okay, understand the logic here? If you want, you can note down some statements here. Count to infinity problem is not a problem. Count to infinity problem is not a problem. For the data packets. Because they rotate only for a finite time. Once TTL value becomes 0, the packet will be dropped, and ICMP will inform by sending time exceeded message. Next statement, the real problem is for the routers filling with the wrong values. And these wrong values are given as input to other routers. So finally, the network will collapse. This problem is known as count to infinity problem. So now for example, I have taken some diagram how to convert that graph into tree using the shortest path algorithm or Dijkstra's algorithm. So suppose you are starting at root router A. So how to start the algorithm? Here the count value will be there before starting the algorithm. So what is the meaning of count? It should know the number of routers in the whole diagram, and obviously you will be knowing easily because this algorithm you apply in the intra domain with it works in a small autonomous system. So the number of routers are in a bounded or in a number will be less. So you can count it easily. Why the count value is required? As you start the algorithm, you will be knowing about it. So from router A you can start. So from router A, what we say that initially from router A to all the routers, the distance is how much? Infinite, you can say. Okay, that means infinite means what? Doesn't know, means cannot reach, you can say. So how to start? From router A, who are the neighbors to router A? You can see B and it is C. Because who are the neighbors? It is 4 and 1. But out of 4 and 1, which is smallest? 1 is the smallest. So you can traverse, that is the C. So this is 1 value. So as you visited a new node, the count value is decremented. Means what? When the count is decremented, it indicates that already 1 node is visited. So at this point, see what you can say, from router A to all routers, the distance is infinite. But at the router C, the distance is how much? It is 1. So you can say from the router C, who are the neighbors? You can say now it is 3. That means D is the neighbor, it is D. So 1 plus 3, how much? 4. But before traversing the path, what the algorithm says, go back to source and find out any other alternate paths are there to reach that router D. If it is there and if that is smallest compared to the existing one, go ahead via that path, or else if this is the smallest, you can continue via that path only. So now see 1 plus 3, 4. To go back to source, it is 4 plus 2, it is 6. So it is largest. So we can continue. So 1 plus 3 is how much? It is how much? 4. Understand? Now with respect to the D, who are neighbors, B and E are the neighbors. But 2 and 9, so 2 is smallest, so you can traverse that and the count is decremented. So you can charge 4 plus 2, how much? 6. But what I told, go back to source and find out any other alternate paths are there to reach that node. Yes, the path is there. Yes, it is smallest, it is 4 only, so you can traverse actually 4. So count is decremented. Now the algorithm is at position B. Then what is the value? It is E. So B to E, how much? 4 plus 4, how much? 8. But go back to source, any other alternate path, it is there, but that value is highest, so you can traverse. So 4 plus 4, how much? It is 8. And the count is decremented. Now the count value becomes how much? 0, because all the nodes has visited. Now what happens? Now this graph is converted into tree using the shortest path algorithm or a Dijkstra's algorithm. Now this router A, if it is sending that LSDB packet using flooding, it will go to all the nodes and all nodes will be updated with a latest value, but there won't be any loop or a cycle problem or a conjunction problem because it is a tree. So that is the advantage of converting a graph into what? A tree. Understand? So this is one problem. Now see, for example, I have taken one more problem. Suppose say router A connected to router B and router C. If this is the graph I have taken, say for example, okay, this is the value, this is the diagram I have given. So you have, this is the A is the root router. So we have to convert that graph into tree. To convert this graph into tree. And in this problem, they have given the metric as the delay. If you can resolve it, it is okay. Or if you find any ambiguity, you can try with a hop as the metric. So this is given in the problem. So here the meaning of delay is this 3, 1, 2. These are the delays. So how to convert this graph into tree? Okay. So from router A, you can start because that is the root router. But observe here it is 3 and 1, which is smallest. So 1 is the smallest, you can traverse via that path. So A to C you have traverse. So how many units? It is 1. Okay, understand? And now we have to traverse to the B and the count value is decremented. So from C to B if you traverse, so 1 plus 2 how much? It is 3. But what I have told, if you can find some other alternate path that go back to source, yes, A to B how much? It is 3. This side is 3 and the other side is also 3. So we are getting a ambiguity problem. So you are unable to resolve with a delay. That's why in the problem they are going to given the one more metric called hop. That means whenever there is a situation, there are two paths are there which is equal distance, they will be giving some other metric to resolve that ambiguity. Okay, so how to solve that? Now you can see A to B, how many hops? It is 1 hop. But here you see A to C and C to B 2 hops. So number of hops are less, in which case left side. So you can traverse in this way. In that way, this graph is converted into tree. So you will not get a loop or a cycle problem. Okay, understand? So this is another model which we have covered. Now for example, see, suppose in a problem, if it is given like this. So router A, okay, connected to router B, connected to router C, then connected to router D. So these are the different links we have connected, and A is call it as the root router. This router A, you can call it as the root router. So these are the different delays that they have given, 2 and 1. What are the other parameters that are given in the problem? Say for example, the bandwidth of this particular link is given as 100 megabits per second, that is A to C. It is given as what? 100 megabits per second. And suppose a C to D is given in the problem as what? 100 megabits per second. The bandwidths are also given in this problem. The bandwidth via this path, this is given as what? 10 megabits per second. And here the bandwidth is given as 100 megabits per second. Okay, fine. So this is the whole diagram. These all are the routers and the different bandwidths are given. So in this problem, what are the other inputs they have given? So try to solve with a delay how to convert this graph into tree. First try with a delay. If there is an ambiguity, try with a hop. If you have still ambiguity, then try with a bandwidth. So this is the order in which you have to follow for converting this graph into tree. So that is given in the problem. So how you can convert? Okay, so from router A is the root router. From there you can start. Now see 1 and 2. 1 is the smallest. So you can traverse, and this is the C. Okay, understand? So it is 1. But here this value is 2, it is largest. So once it is traversed, count value will be decremented. Understand? So this is 100 and this is 100 and this is 100 and this value is how much? It is 10. Say once it is traversed. Now see from C to D, if you traverse 1 plus 2, how much? It is 3. Go back to source. If you go back to C, 2 plus 1, that is also, in the meanwhile, you can traverse this path. That also becomes 3. Okay, so if you go in this way, it is 3. The other side is also 3. You are unable to resolve with what? Delay. Then you try with a hop. What is the meaning of hops? See, from here 1 and 2. Here 1 and 2. So both sides it is equal. So hop also you are unable to resolve, because you can see 1 and 2. Here also 1 and 2. 2 hops both are equal. So with hop also you are unable to resolve for this particular D. So then you have to go for what? Bandwidth. See in the problem, that's why bandwidth is given. You can see from A 100 megabits per second, 100 megabits per second, but from this side 100 and it is 10. So 110 and this is 100, 100. So which path you have to go? So it is 100 and 100. So this is the answer. But you can ask, in case of delays, you go for the smallest. But for a bandwidth, why we have to go on for the largest value only? It's quite simple. Bandwidth is high, then transmission time formula, data size upon bandwidth. Bandwidth is high, denominator is high. Denominator is high, oral value will be less. Oral value is less, time is less. You can transmit fastly. That is the reason in case of bandwidth, you go for the highest value. So the graph is converted into what? The tree in this way. So like that, the particular graph will be converted into tree using shortest path tree algorithm, and a LSDB packet will be given to all the routers. You will get the latest information periodically, okay, time to time. So there won't be any count to infinity problem in case of this link state routing. But in distance vector, we got a problem called what? Count to infinity problem. But both this link state routing and in the case of distance vector, both are intra-domain routing protocols only. They will work only in a small area called what? Autonomous systems. Okay. Okay, see in the distance vector, we got a count to infinity problem. So we are going with one special case called distance vector split horizon. Let us try to analyze what exactly mean by that. Suppose see we have taken some diagram. These all are the routers. Router X is connected to router A. Then connected to B, suppose say some K. So these all are the different routers connected with the cable. So let for example 1, 1 and suppose say 4. These all are the delays. So a packet came to router A. Okay, this is a case 1 and asking that it want to go to X. Initially all the tables are empty, but every router will be knowing the information of the directly connected router. So A knows that it is X is directly connected. So it's going to update the table X. How many units? So it is 1. Who is the mediator? Nobody. So the packet will go to destination? Yes. So the table is what? Correct. So case 1 it is working. Okay, like that. Now let, for example, after that, in case of case 2, in fact you can write it as a case 2, packet want to go to X. At that time, what you will do, you can see with respect to B, A and K are neighbors, you can say directly connected. Anyway, K cannot give any information about X, but it will tell you that I am connected to you at a 4. So whatever this B asking, that X is not, I mean, what I would like to say, whatever this X is asking, this packet is asking, K cannot give any information, but from this side, A can give the information about X. So A is telling to B that I know how to reach X, how many units? 1, and that information will be given to B. Then what does B will think? If I can send this packet to A, who will take responsibility? A, and it is going to update the packet. What is the table? X, 2 units, because 1 plus 1, 2. Who is the mediator? So it is what? A. Okay, understand? So from here, the packet, it will go to A, who will forward it B, but from here A will forward, the packet has reached to X. Yes, so this table is correct because the packet has reached to the destination. So that is case 2. Say for example, in case 3, so packet came from outside, so packet want to go to K, and this is the third case. With respect to that, you can see for B, this K is directly connected. So it's going to update the table. How it's going to update? K, how many units? It is 4. Who is the mediator? So nobody, so it is a dash. So the packet will be forwarded to K. Yes, so this table is also correct. So everything is working fine. But where we got a problem, if you remember, in case of distance vector, when a link is broken, you got a count infinity like 2, 3, 4, 5, so on. It is becoming a unstable values, you can see. Now here let us go to with a split horizon concept. Whether it will solve or not, let us try to analyze. See the same thing, X is connected to A, then connected to B, then connected to K. This value is how much? 4, 1 and 1. And at this point of router A, the packet came, okay, and this is the case 4, you can say, the case 4, and the packet want to go to what? X, and at that time the link is broken. Okay, fine. Now what happens? Case 1, case 2, case 3 are working. In this case 4, a packet came to router A, and at that time the link is broken. So tell me here what happened in previous situation. Since the link is broken, the only neighbor is B. So B has told I know how to reach X as 2. So 2 plus 1, 3. 3 plus 1, 4. 4 plus 1, 5. 5 plus 1, 6. So on like that. And the packet is rotating in that way. So that is called a quasi state or unstable state. That is what exactly happened. Now see what will happen, because now we are adding some term like a split horizon. What does that split horizon says? That see when a packet came for A, no doubt the neighbor is B. Okay, but what this split horizon says it is? Okay, what does this split horizon says it is? When this B is giving the information to A regarding this table, what split horizon says? Don't send the entire table, okay? Send only the part of the table. That's called splitting the table. That means what does it says? When the packet came and the link is broken, this router B will send only the information about this particular entry only. Okay, but this information you should not send. So that is called splitting the table. So what happens for A, you will get this information, but this information is regarding K, which A doesn't require, because A requires regarding what? X. So whatever A is getting from B is no use because it is asking for X. On the other side, anyway, it is link is broken. So if you don't get the information, then A is going to update that it is X infinity. Okay, understand? So it is a dash. Why? What is the meaning? It is telling, A is telling, I cannot reach X. A to X is how much? Infinity. The meaning is what? I cannot reach. That is true only now, because the link is broken, it cannot reach. Why? A has placed the value A to X is infinity. It's quite simple. Since the link is broken, if the link is not broken for A, X is a neighbor. Since the link is broken, the only neighbor is B, but B is giving the information only about this K but not X. That is what split horizon says it is. But first point what you can ask, why this information is not sent by B? What split horizon says that don't send the root information back to the node which you have learned from it. Don't send the root information which you have learned from it. Now observe here, B learned about X as 2 with the help of A only. So how can this B send back the same information back to A of which B has learned previously? That should not happen. Okay, so that is what split horizon. That's why this information will not send. Only this information will be sent. Once again, see, B has learned about X as 2 with the help of A previously. Then when you learn from A, then how can you send back again to A? That should not happen. That is what split horizon. What is the definition of a split horizon? Means what you say that don't send the root information back to the node which you have learned from it. So that is the happening. What is the understand? Other side the link is broken, other router is giving the information which is not required, then it is going to place the value as infinity. So the packet will be dropped here only. Okay, so it's correct only, yes. But what happened previously when the packet came? This value is updated as a 2 plus 1, 3, packet has moved here. 3 plus 1, 4, packet has moved here. Like that, unnecessarily packet is rotated for a finite amount of loop. But now it is not happening. Understand? Now, what is happening now? Here, next time when the packet came to be asking for X, infinity plus 1, it becomes how much now? Okay, next time a packet came to be asking for X, infinity plus 1, it becomes what? Okay, X infinity. With the help of whom you have learned? A. Is it clear? Have you understand the logic? So it is correct now. B also know that I cannot reach X, and that is done with the help of A. And the packet will be dropped here. And the next iteration, suppose a K also will be knowing, you can see infinity plus 4, it is infinity, X infinity. But how does K knows? With the help of what? B. Like that. So everybody knows that this link cannot be reached. So this is how we are able to solve that problem, you can say. But here one important point is, once a link is broken, first who knows about it? A knows. Or when the link is broken, A, B, K, all the routers know immediately at the same time. Answer is what? No. First who knows? A. In the next iteration, B. In the next iteration, K. So here one important point is, distance vector routing, whatever we have learned, is a slow convergence algorithm, because it is knowing slowly one by one regarding this link is broken. Or you can say when a link is broken here, it is taking big O of n time to know to all the routers about this broken link, where n is the number of routers. That's why you can also call it a slow convergence algorithm. Now this count infinity problem is solved in the link state also, but when the link is broken, it is known to all routers immediately because you are applying there the flooding algorithm. So that's why that is called fast convergence algorithms. So here what is happening? It will know, it will update, then that update information will send to next router, then to next router. So here we can say, in case of distance vector is a slow convergence algorithm, whereas in the link state routing, it is a fast convergence algorithm, because it will be knowing to all routers immediately, because there you are applying the flooding.